Hello everyone, my name is Madhav Kumar Joshi and I am from AML section A. So today we'll be tackling one of the most difficult problems in computer vision and image segmentation. So if I show you a picture of a crowded street, you don't just see traffic, you see car A, car B, pedestrian, road, sidewalk, etc. You instinctively know where the car ends and the road begins. For a decade, computers couldn't do this. They could only put a crude box around the car. Today, we'll discuss how it taught machines to see the world pixel by pixel. So, the hierarchy of the vision. Let's formalize the hierarchy of task. So, the first is classification. There is a balloon in the image, say global label. Then comes object detection. The balloon is here, bounding box. Then semantic segmentation. These specific pixels are balloon colored, so there's no distinction between two balloons. Now fourth is instance segmentation. Balloon A versus balloon B, distinct objects. So then the last is panoptic segmentation, the unification of everything, classifying the background stuff and foreground things. Now let's come to the historical struggle. Why was this hard? Early attempts used sliding windows. We took a tiny 10 by 10 patch of pixels, fed it into a classifier, moved it one pixel, and repeated. For a standard 1080p image, this would require 2 million forward passes. It was computationally impossible. We needed a way to process the entire image at once. The semantic revolution. The all convolutional shift in 2015. Fully convolutional networks (FCN) were published. So the insight, they realized that dense layers destroys spatial information. So the fix to this was that they replaced dense layer with one by one convolutions. So as a result of which the network became a dense heat map generator. It could take an image to any size and output a segmentation map of that size. This way, the Big Bang moment for segmentation had occurred. Now, the receptive field problem. But the FCN had a flaw. It could not see the big picture. This is a concept called receptive field. If your convolution filter is 3 by 3, it only sees 9 pixels. By stacking layers, we effectively zoom out. However, classic pooling loses resolution. We faced a trade off. Do we want high resolution or high context? We couldn't have both. So, Google's Deep Lab solved this with dilated convolutions. Imagine a filter that expands like a net, it skips pixels. It allows a 3 by 3 filter to cover a 15 by 15 area without adding parameters. This allowed networks to understand global context. For example, this gray pixel is an elephant because I see a jungle around it without losing the resolution needed to draw the trunk perfectly. Then comes the architectures of choice. The unit, the medical gold standard. While Google focused on natural images, the biomedical world needed precision. then enters the unit, the encoder decoder structure. The left side shrinks the image or captures the context, and the right side expands it or localization. The critical component, the skip connections. Analogy. Imagine trying to reconstruct a face from memory. You might get the general shape right, but you forgot the exact shape of the scar. The skip connection is like having the original photo right next to you to copy the details from. Now let's look at a specialized variant, VNet. In medical AI, for example, for CT scan or MRI, data isn't 2D images, it's 3D volumes or voxels. VNet replaces 2D convolutions with the 3D convolutions. The math is identical, but the computational cost is skewed. A 3 by 3 filter becomes 3 by 3 by 3 filter. This allows the model to understand that a tumor continues across multiple slices of an MRI scan. Then coming to instant segmentation or mask RCNN. For self-driving cars, knowing this is a car isn't enough. We need to distinguish car A from car B. So mask RCNN adds a third branch to faster RCNN. Branch 1, for example, branch 1, is it a car, which is class. Branch 2, where is the box? B box. Branch 3, which pixels are the car? Mask. So the align comes as I want to emphasize ROI align again without this mathematical trick of bilinear interpolation. The mask would be jagged and misaligned. Now coming to the modern era and foundation models. The transformer takeover. Since 2021, CNNs are being replaced by the transformers. Convolutional neural networks or the CNNs look at neighbors, locals, but transformers use self attention to look at everything. It's global. Segformer is popular architecture here. It chops the image into patches like puzzle pieces and lets them talk to each other. Now you must be thinking why it's better. A convolutional neural network or CNN struggles to link a tail to a cat if the cat is huge and occulted, occulted. But a transformer sees the tail and the head simultaneously and connects them instantly. So hence a transformer is better than CNN. Then comes the segment anything model or the SAM. The biggest news in 2023 was Meta's segment anything model or SAM. So until now, models were specialists trained only on cancer cells or only on cars. But SAM is a generalist. It was trained on 11 million images with 1 billion masks. So it's a promptable segmentation. You can just click on an object or draw a box and the SAM segments it instantly. It doesn't even need to know what the object is. just knows that this is an object. This introduces zero sort transfer. You can use SAM to segment underwater ruins or microscopic bacteria without ever training it on those images. This is the ChatGPT 4 moment for computer vision, or like GPT-4 moment for the computer vision. So, coming to the engineering and deployment, the loss functions, the math of imbalance. How do we train this beast? Problem, class imbalance, 99% background and 1% object. So, cross entropy loss fails. It gets overwhelmed by the background. Dice loss and focal loss. This mathematical term downweighs easy examples. It tells the model, stop looking at the sky. I know it's sky. Focus on the confusing edge of the bicycle. Now the real-time constraints. YOLO and mobile nets. Mask RCN is accurate but slow, 5 fps. A self-driving car needs 30 to 60 fps. We use YOLO segmentation or mobile net backbones. We convert the math from 32-bit floating point to a 8-bit integer. We lose a tiny bit of precision, which is like 0.5%, but gain 4x speed up on edge devices. If you want to work in this field, know this. Data is the bottleneck. Bounding boxes, 5 seconds to label. Segmentation marks, 50 to 80 seconds to label. We are moving towards synthetic data to bypass human labeling entirely. So let's summarize this entire journey. So we have covered 10 years of history in around 15 minutes. So the FCN gave us the first heat maps, the UNet and the deep lab solve resolution and context. Mask R CNN gave us individual object instances, and transformers and SAM have given us universal understanding. So, my final thought would be the future isn't just about better accuracy, it's about video segmentation and 3D world reconstruction. And as we are moving from labeling pixels to understanding physics, so thank you for your attention, and I'll be winding up this topic. So, I'd also like to add that image segmentation has evolved from a clumsy sliding window into a system that rivals the human eye. We have moved from detecting boxes to understanding pixels, and now to understanding the concepts. The camera is no longer just a sensor that captures the light, but it is an intelligent agent that understands the world. So, by this, I would like to conclude this seminar and this topic. Thank you for your attention. Have a nice day.